recording. Okay, so we're starting the recording. We want to find a power series representation for this function f of x equals x over the quantity 1 plus 4x squared. Okay, so what makes this problem a little different from the others that you've seen? What makes this problem a little bit different? A little bit harder, maybe, you might say. How is this problem different? That's right, Josiah. The denominator is squared. And we can't, just by simply rewriting this function, the squared in the denominator can't be like easily removed. So what we're going to do is we're going to explore finding a power series for 1 plus 4 over x without the square. And then we're going to do something. So, okay, let's look at that. So, okay, 1 plus 4 over x is the same as 1 over 1 minus negative 4x. And we write that as the sum of n equals 0 to infinity of negative 4x to the nth power, because negative 4x is our apple. The interval of convergence is going to turn out to be from negative a fourth to a fourth. Okay. And we're going to take that negative fourth times x raised to the nth power, and we're going to write it as negative 1 to the nth, 4 to the nth, negative 1 to the nth times 4 to the nth times x to the nth. And you're going to see why we want to do this in a moment. Are there any questions so far up to that step there? Okay, so our original function was x over 1 plus x over the quantity 1 plus 4 over x quantity squared. Here's what we're going to do. We can take the derivative of this 1 over 1 plus 4x. We can differentiate that, and by differentiating it, we'll be able to relate it to our original function. Because the derivative of 1 plus 4x to the negative first power, okay, the derivative of that is equal to, by the chain rule, negative 1 times 1 plus 4x to the negative second times 4. Okay. And so the derivative of 1 over 1 plus 4x equals negative 4 over the quantity 1 plus 4 over x quantity squared. So we're trying to end up with something that we can relate to the original function. Okay. Let me pause for a minute, let you copy that down, see if there are any questions. I want to make everything visible here. All right, and Dr. Carbone has joined us. Hello, Dr. Carbone. And Dr. Carbone sent an email out, by the way, about his study session tonight from 8 to 9.
Good afternoon.
Good afternoon. Students are enjoying these section 8.6, Dr. Carbone.
Oh, that's great.
Yes. All right. Well, so remember our original function here. We're trying to get a power series. For this function. Okay. And, well, all right, so we're not too far away, right? We're not too far away. The derivative of 1 over 1 plus 4x equals this here, negative 4 over 1 plus 4x quantity squared. And then our function is different by a factor. And we can deal with a factor. So watch what we're going to do here. Remember, 1 over 1 plus 4x, we have a power series for that. So this derivative here, negative 4 over 1 plus 4x quantity squared, is equivalent to the derivative of this power series. I mean, it's equivalent, it's the derivative of 1 over 1 plus 4x, but that can be thought of as the derivative of that power series. So this is certainly a true statement. Negative 4 over 1 plus 4x quantity squared equals the derivative of the power series. Okay. Are there any questions so far? All right, well, the derivative of a power series, the power series is a sum. So if you have the derivative of f plus g, that equals, of course, f prime plus g prime, right? The derivative of a sum is the sum of the derivatives. Well, we have the derivative here of a sum. So the derivative of a sum would be the same as taking the sum of the derivatives of each of the functions. For every different value of n, you have a different function here. So certainly, this is true. Are there any questions on that? Any questions? How many think it's kind of beautiful? Tell you what, maybe I'll wait till we finish before you answer that. So look, we have the derivative of, with respect to x, of this negative n negative 1 to the nth power times 4 to the nth power times x to the nth power. We can treat negative 1 to the nth power and 4 to the nth power relative to x. They are treated as what? What are negative to the nth power and 4 to the nth power treated like relative to x? Good, Robin, constants. So we can bring those out. We can bring negative 1 to the nth power and 4 to the nth power out in front of the derivative. And then the derivative of this x to the nth power is just n times x to the n minus first power. Okay. Now we're going to get to this next step here, but are there any questions so far up to this step here? All right. All right. Well, so with power series, sometimes mathematicians want to re-express the power series in a nicer way. Power series, how you express them is not unique. Here, for this series here, this series starts at n equals 0. But what if you instead wanted the series to start at n equals 1? Okay, what if you wanted that? Let me just see one moment here. Oh, well, actually, hold on. This series here, the series from n equals 0 to infinity is the same, is equal, let me just hold on. This series here is the same as this series. In other words, the series on the left starts at n equals 0. The series on the right starts at n equals 1. Oh my God, well, how can those two power series be equal? How can that be? I mean, how can that be? Does anyone have an idea? So what they're saying is basically the first term doesn't matter, right? When they say the series starting at n equals 0 equals the series starting at n equals 1, what does that mean about the first term? What would the first term have to equal in order for these two series to equal each other? What would the first term of the series have to equal? Let's think what the first term of the series, that's right, Josiah, 0. And look, when very good, and when n is 0, if I put in 0 here, okay, thank you, Dr. Carbone, for the chat announcement there about your session tonight. If I put in 0 for n here, right, this is when n equals 0, it's the first term. So when that's the case, you get negative 1 to the 0 times 4 to the 0th power times 0 times x to the 0 minus 1. So the first term 0, so these two series are the same. But now what they do is they have a series. The series starts at n equals 1. But then what they do is they take this series and then start it back at n equals 0. They're starting it back here at n equals 0. They must like it to start at n equals 0. And you know, in WebAssign, sometimes, like if you have, for instance, a free response or like a multiple choice answer, they might have the answers. You might work a problem out, and your power series might not be exactly the same as one of the choices. So in that case, what you have to do is manipulate your power series, so rewrite it in another way so that it matches one of the choices. Here what they're doing is, when n equals 1, to go to n equals 0, you have to make an adjustment on all the n powers by adding 1. Because when n equals 1, for instance, the first term is going to have negative 1 to the first. Well, if you want negative 1 to the first to be in the first term when n is 0, you have to adjust your n power to n plus 1. So anywhere you see an n, you're substituting an n plus 1. And of course, well, yeah, that's right. That's exactly right. And n minus 1, well, n plus 1 minus 1 is n. So that's how you get the n there. Are there any questions so far? We're not far away from finishing this problem. But manipulation of power series is very important. When you take differential equations, you'll be solving differential equations using power series solutions. And there, manipulation of power series, working with the indexes, changing the indexes so they match, things like that are very important. So, all right, I'll move to the next page if there are no questions. All right, so we've established that negative 4 over 1 plus, over negative 4 over the quantity 1 plus 4x squared equals this power series. So now let's go back to the problem. Here was our function, x over the quantity 1 plus 4x squared. The negative 4 over 1 plus 4x squared, I have a power series for that. We have a power series. We just derived it by taking a derivative. And I can substitute in that power series right here. But naturally, and you can see why. Incidentally, let me just go back for a moment. You can see why in this example, why it was helpful to get the 1 over 1 plus 4x in simplified form, because then it was easy to take the derivative of the power series. Okay, so that's why we want things in simplified form, our power series in simplified form. Okay, so f of x is equal to x over 1 plus 4x quantity squared. I'm going to substitute in the power series for negative 4 over 1 plus 4x squared. And then I'm going to bring in the negative x over 4, because it's a constant relative to the sum. And then I'm going to try to simplify this. This series here can be simplified. Are there any questions up to this step? We're almost done here. Okay, well, so negative x, right, is equal to -1 times x. So -1 times -1 to the n plus 1 is -1 to the n plus 2, right? Because, and then that x there times x to the n is x to the n plus 1. So hopefully you're seeing where all these come from. 4 to the n plus 1 divided by 4 is 4 to the n. And you have the n plus 1 here. So you see in, right. Are there any questions? We're going to do one more step then. All right, so this is a perfectly acceptable answer, but maybe like in WebAssign, when you're working on your homework, maybe you don't see this particular answer there. Maybe you see this answer. Okay, maybe you see this answer. So this answer looks exactly the same. This answer, the last power series, looks exactly the same as the power series previous. It's just instead of getting -1 to the n plus 2, you have -1 to the nth. But you can say that's true because -1 to the n plus second power is -1 to the nth times -1 squared. And -1 squared is a positive 1. So it's just in a little bit, this is a little bit nicer form, the last form. All right, are there any questions on that? Who's comfortable? Who's comfortable with that? With what you saw here? I know it takes time to absorb, but I might sleep a little better if I know, maybe some of you are. Okay. I hear you, Julia. Kind of. Julia says kind of. We'll need to look back over it. Okay, very good, very good. Thank you, Robin. Thank you, Josiah. All right, great. Thank you, John. All right, well, very good work today. Your classwork was excellent today. I'll activate those 8.6 exercises so you can continue working on them. And great class today. I will log out of this class session, and if you have any questions, I'm going over to my office hours session. Thank you very much.